So, in the previous class, you saw that we developed a comprehensive code in MATLAB that I shared with you via emails. We had different disturbances you can see here. This D for different time intervals, and then after simulating, we did a movie of that together in the coding. Uh, for saving the class time, I added the lump mass at the end of the pendulum. Let me teach you from the high school. So not even university. So in high school, if this is pendulum, guys, this is pendulum that we drive everything and from the. So I added this lumped mass at the end of this. How I did it? Uh, I'm gonna just make it bigger to show you. Okay. This is a pendulum that we control by PID controller, theta. Then, from high school, a point on the circle, in X and Y, gonna be this, see, point P, point O, okay? So how much is here from high school? It is L. It is L sine theta for point O. How much is here? This is X of that. This is Y of that is L cosine theta. Now I'm going to say angle here phi for the circle. I'm going to plot the circle when it's moving. So X of P gonna be X of O plus R, radius of this circle, R, this is high school, R cosine phi, Y of P on the circle, I have Y of O, R sine phi. Everybody agree? Right? Everybody?
Yes.
So X of P gonna be X of O. X of O is this L sine theta plus R cosine phi. Y of P is L cosine theta plus R sine phi. But your phi, if you want to generate a circle, is between 0.1 to 2 multiplied by pi, from 0 to 2 pi. Here we go. I just typed this in MATLAB code, saving class time. So we control the system. We are in the, see here? I'm saying this is the radius of the circle. Here we go. Because I'm going to reshare again with the radius of the circle, and this is rotation angle phi, as I told you. Exactly I type here inside the for loop. X of c, L sine theta. Theta is from above this, right? Angle of the pendulum. Here we go. This theta. See here. But here you have to put K because this is moving. That's right. K and 1 and RC cosine phi. Exactly as I did. Then when I type this, let me write here because I'm going to share with you. These are X and Y of the point on the lumped circle of pendulum. Okay, I've just added this fill XC, YC, and red. Also, I added the second here for the text for T, means second. Now, if I run this, guys, you're gonna notice this. Here we go, guys. Do you see this, guys? Exactly, I plotted this. We're controlling at going to 60 degree eventually. These are disturbances affecting. And I added this second here. Let me move it here. See this second here. That comes here, second, exactly as I type. So that's the first disturbance gone. First disturbance was between 1 and 3 seconds, was 50 a constant, then between 4 and 6 ramp, we are still between 4 and 6 see ramp, then between 7 and 8 a harmonic disturbance. But our controller is very strong and finally goes to 60 degree. I want to stop at 9 seconds. Okay. There you go. So this harmonic disturbance. Oh, I have to change this around. This is harmonic. Wait, if I said parabolic. Oh, previously was parabolic. And 8.5 is gone, and now it's going to 60 degree eventually. Almost 60 degree. So you saw it. But now suppose I want to control a painting robot in the car manufacturing system that the base of that is moving. Base of that is moving. So the disturbance is the base, not can be say disturbance, but the base is moving, and I want to push this angle here, and I want to control that. Okay, so let me stop it here. So let's go for one degree of freedom painting robot as a pendulum. Okay, so not here. I just only changed, guys, see the control input, see the force is doing control input, and I take it out from semi-lag. So this is the error signal, and finally goes to 0. See that with different disturbances, and then you saw it previously. You see the angle of the robot goes to 60 degrees. So let me go there. Well, I promised you at the beginning of this course in the second class, I think, that okay, now let's go and control this. I'm saying simple painting robot in car manufacturing system. Painting robot as pendulum, huh? Suppose your painting robot is 1 degree of freedom system. When you go to robotic class with me or Dr. Ahmed Abadi, we're gonna teach you there for 2 degree of freedom robot system. Okay, so so this is the pendulum, but this base is moving. X of t, suppose, is sine of t as harmonic. Gonna move like this, ding, 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 painting robot. So this, I want that move from here to say 45 degree. Theta d is 45 degree. So only disturbance, and I'm gonna apply a control command U here at the joint to give us 45 degree. And suppose this is the area on the surface. So when it goes to 45 degree, it's gonna paint this eventually. Paint this area for me. So this is the problem. But I derived the equation of the motion for you previously. If you look at your notes, it's theta double dot plus G over L sine of theta was minus X double dot base motion cosine of theta over L plus U, the control input now this time. Let me change you have your notes, I'm just adding the U here. If you derive, gonna be like this, U ml square. But remember, our M for simplicity is always 1 kilogram of this robotic arm, 1 degree of freedom, and L is 1 meter. Being said, for teaching purposes, you're gonna be plus U. So our our state space equations for the linearized system is going to be exactly the same before, except the M2 going to be minus G over L M1. The previous one I'm going to show you was plus, here's minus, plus U. That's right. Minus X double dot. I'm saying X double dot as disturbance. I'm saying this is disturbance. And this is going to go 1 for linearized system. So I'm going to be 1. Oh, I have to remove it. I talked to linearization, and L is 1. Forget about that. So the equation is going to be this for linearized. Here we go. And here you have this minus, comes here, minus. I derived this already at the beginning of the semester for you, because I knew I'm going to use it one day in the control. So what I'm going to do, I'm going to copy paste everything from here, generate a MATLAB code I'm going to share with you. I'm going to say here the name is different. PID paint robot. Paint robot. And I'm going to make it 2 because I want to just only linearized version. G is 10, L is 1. I'm going to keep it still here. I don't change the gains until now. So the only disturbance you have, I said, is D. Here we go. D. So I'm just commenting here, guys. I'm saying D is sine of T. But, I'm sorry, X is sine of T. X is sine of T, which is base motion of the robot. Okay. So if that's the case, we need X double dot. X double dot is how much? X dot is cosine theta minus sine theta. Gonna be minus sine T, minus sine T. This is the base motion of the robot. Still, I'm gonna push it to this time 45 degree. Desirable input. I'm not changing everything except I'm removing everything for nonlinear terms. I'm gonna make it nonlinear terms also from here. Okay, and we don't need this also because I'm gonna keep it simple. Only difference is we have minus D. See here, because it's pendulum, not inverse. Minus D linearized. Minus G over L M1. See, previous one, G minus, because L is 1, that's right, you already know it. Minus G M1 plus U1, obviously. So this is in between the inverted pendulum as robot and the regular pendulum as robot, but with the base is moving. And also I'm gonna copy and paste here, and I'm gonna save it as paint robot solver. Okay, solve. I'm gonna name it. I'm gonna just close those, do not confuse. So we don't have nonlinear terms here to be global. I'm gonna share with this, guys. Everything is the same except that we have 2 state variables, M1 and M2. I'm not comparing everything together. There is no need for this. The same, no need for this. No need error signal of this. Good. And this is plot of only not this, U. Okay, now I'm gonna put this as comment to see that what is this E? No. So I'm gonna make it comment the movie first to make sure our controller works well. Hmm? Oh, there's no 3. 1, 2, UP. Yeah. So here we changed this sign of G theta or GM1 compared to inverted robot. So, and this is linearized painting robot. It's very simple white version. Painting robot. Okay. Everything is fine. I'll tune this later. So let me see what we will have. Oh, I have to call this time. There we go. Okay. Well, let's see what we have. Okay, I don't care about you. And error signal goes to 0. I'm 45 degrees. It works well. Our tune previous. I'm not changing because I'm going to save the class time. See that even that's the base moving. This goes to 45 degree. And let me rerun it again, guys. And use this. You can tune more to reduce U. When you go to grad school, linear system theory, they're gonna teach you LQR control to minimize U, okay, as a cost function, not here. So the signal goes to 0, and here we go. Okay. So now let me go and make the movie run, because I'm gonna show it. Control T. Okay. So this is x of s, but this is for the square. Remember, square one. Now you have to add plus these guys. Get here. You have to add. What is that? You have to add x is equal to sine of t. Sorry, because it's under that harmonic force, harmonic displacement. So here you have to add, say, sine of your t here, guys. This t. Your t of kn1 every iteration is right, kn1. So I have to, oh my god, kn1. Bear with me. So your x must goes inside this time, or the square. All x's moving with that. See, plus. Oh, two pluses. The base x's move with the harmonic terms, right? As I told you, look at here. Your x is sine of t. Double derivative, we put it here at minus sine of t. That's right. So I want to make sure that this time minus again. Okay, good. So 0.1 and oh, you see what I'm doing exactly? The base is moving as sine of t in every iteration. Here we go. So x of c. Let us see what happens. Okay. Let me run this. So this is gonna be, oh, here you have to put like that. Uh, yeah, you have to put this. But to define this as this base motion instead of doing this. Base motion is this. So I'm gonna add here as BM base motion. BM BM BM. So here gonna be not 0 anymore, guys. This is moving, so you're gonna not 0. BM, this plotting line, that's right. BM, and this is Y. Y is correct. Then what is this? 0. Oh, okay. This X is gonna be M because BM is changing. Y of S is fixed, good. Okay. X of C is BM plus L sine theta plus this. Here we go. Oh, only X, I think. That's right. Yeah, L sine theta. Now let me run the. Oh, and here is minus L because it's under that. You can see here, guys. L sine theta minus this, minus L cosine theta. Now I see that. Here we go. L sine theta. Oh, Bm plus L sine theta. Bm plus L sine theta. Here we go. Oh, that's good. X of S, we changed it. And the Y of is same. X of C, we changed it to yes. Let me run to debug it. Oh, there's something wrong with here. I have to fix the circle. Oh, obviously I know why. This is downward. X of C, Y of C is minus this plus, I think so. Yes. Okay. Now let me change the direction. And it's gonna be minus L. Everything I'm changing. And here minus 1.6. Minus 1.3. Oh, that's right. Here we go, guys. Base is moving, and we're gonna keep it at 45 degree eventually comes as sine of phi. So we control the robot, the painting robot. You got it, everybody? Yes? Yes, everybody? Yes. Good. So despite the base movement of the robot, see now the robot is converted, it's gonna paint this area, say. Paint this area, this line, for example. Just imagine. At 45 degree. There we go. We have it. Okay, now gonna tell me payment in the most of car painting robots. This is very simplified version, guys. I would like to have desired like this. The base moves and also the pendulum moves. So your trajectory, your set point is sine of t. So if that's the case, your theta dot, okay, gonna be cosine of t. Because differentiation of this, that's right. Our desired is not 45 degree anymore, okay? Sine of t. I want to see that this tune numbers follows that. It's gonna be very easy. Okay, let's see. Now, see, the robot is covering area, supposed for painting, that's right, sine of t. Gonna oscillate by itself. How we know that it follows? Look at the graph. Look at the graph. Look at the control input, guys. Okay. There we go. Oh, I have to compare this with the sine. Bear with me, guys. I have to plot t and sine of this. So multiply. Actually, this is in radian, but I'm not why I'm comparing this with that. Okay. So this is what we want: desirable angle sine. What's wrong with this? Okay. What? You don't have variable sine? Oh! Sine of t. I'm sorry, guys. Exactly, see, it's following this. You are all laughing, exactly. With this KP and KD, exactly follows what you want. Sine. See that? Blue and both of each other. But typically we don't do that. We're not stupid. We want to go to set point or regulation, we name it in control. This is a regulation problem. We are going to a set point, okay? And let me remove this and keep it as, we don't have this. Oh, what I have done. One 1.2. Why I remove this? Oh, I see that now. And I wanna change this. Yeah, 54. Okay. So now the base is moving and everything is can be done like that. So now I'm very comfortable after graduation. If you go to grad school, if you deal with the nonlinear controller, you can use this template of the code and embed every nonlinear control as you are doing here by the ODE command. By ODE command. Okay? Just bear with me. So, but there are some specific guys, design of PID, like as the Ziegler-Nichols. These are for very, very specific version of problem. We can't find everywhere. I even don't want to teach you, but I'm gonna just hint because I have to go to the book. There's a table. Let me find it first because I cannot memorize the tables. Yes, 567. Yeah, here we go. So we are done with this. I'm going to share it with you. Okay. Now let's go to what I promised as the Ziegler-Nichols for designing the PID controller. It's very specific, very narrow, but I'm just hitting you one of them. So it says, if to a control system, guys, you apply a step input, a desirable input, step input, and it behaves, the output behaves as a delayed first order system like this. We name it as S-shaped response. S-shaped response. This is Ziegler-Nichols criteria. Ziegler-Nichols criteria to tune PID gains. So you know that when I was teaching you the transient response of first order system, it was like this. Remember, this is the first order system. Now, if you put delay, if you remember, it's going to be like this. It means that the right delaying that. That's we name it as the S-shaped response. Delayed. This is like the delayed. I'm writing here. Delayed first order system. You can assume this as delayed first order system. Now, in this inflection point, if you have such a system, that this is considerable. If you plot an inflection point, if you plot a tangential line, it's gonna cross these two. This area for the delay part, we're gonna say as L. This area, and this is time, and this is output of the system Y, obviously. This area, this value, gonna be T, by measuring. And this is K value, whatever it is, step response. I didn't say unit step, I said step response. K can be 75 Fahrenheit of your room, can be 65 miles per hour of your car. You want to set point, that's right, set point. By saying that, you can say output over U, that's right, can be modeled as K E minus LS divided by TS plus 1. Okay, TS plus 1. Because this is your U. Remember the block diagram? U goes to the plant, and this is gonna be what? Y or C. Let me say Y. Y because it is Y. So this comes from the PID, that's right, from your controller, C controller. Having this, I'm going to teach you now in the MATLAB how to having this in MATLAB. L, K, and T. Ziegler and Nichols, they proposed a table to tune those gains. I'm going to plot it here exactly. There we go. Very, very rare system they have such a step response profile S-shaped, but I have to teach you. Here we go. Here gonna be type of controller, KP. So when I say KP, guys, your book says transfer function of the controller as this. Look at here, guys. If you go to your book, it's going to be KP 1 plus 1 over TIS for integrator plus TDS. This is how you define your PID controller. This KP is being multiplied by all of these, okay? KP, TI, and TD. These three values. And now it depends on that you want to have only P controller or PI controller or PID controller. If you want to have P controller, your KP gonna be T over L. This T over L by measuring. TI gonna be infinity because 1 over infinity is 0 and TD gonna be 0 because you wanna only have P controller. If you wanna have PI controller, your KP gonna be 0.9 T over L. Your TI gonna be L over 0.3. Your TD is 0. If you wanna have PID controller, this is pretty standard. Gonna be 1.2 T over L to L 0.5 L. Bingo. You got it, everybody? Good. I remember, let me give you an example of this. This is another criteria you can find in the book. Is pretty standard. Okay, but let me go to MATLAB. Why I close the MATLAB? Okay, to show you how to do it. If you face industry or wherever you go with the S-shaped file profile of this, so how to do it? Just bear with me until it comes up. Okay, guys, if I remember, suppose your num, as I taught you, is 0, 0, 0, 1, a third order system. Hope that, and then is 1, 3, 3, and 1. And if I plot step response of num and then, it must show the S-shaped profile, if I'm not wrong. Yes, it does. Okay, it does. See the S-shaped profile. Okay. Now, what you're gonna do, you're gonna insert a line. How are you gonna do that? This is inflection point, and this is gonna cross here, just bring it down until it goes to an inflection point in MATLAB. I'll say, and you can, here we go, and then you can continue this line until it goes slowly, almost here, okay? So now obviously you have k value. Look at here, k value here is how much? 1, right? K value is 1. So I'm writing here for you. So your k for this step response of the system here is 1. And now your t value, your L value between here and when the delays happens, like exactly not like this here. So say here, and let me zoom in this to find those. There we go. How much is here? What? What the hell is going on? I want to see how much is here. Oh, okay, 0.4 almost, huh? Yeah, no, what's greater than that? Why is not doing that? Let me stop this. Almost 0.69, say. So your L value is 0.69 almost. And your T value is 0.69 to almost 4, huh? 4 minus 0.69 or 7. So your T here, your T is say 0.7, huh? T is 3.3. Here we go. Now suppose I want to design PID controller, huh? So my GC, gonna be this, my controller gonna be 1, this is 1 plus 1 over, I'm sorry, not 1, I'm getting older. So gonna be, so here we go, this 1.2 T 3 over 3 divided by L 0.69, 1 plus 1 over TI, TI is 2L, 2 multiplied by 0.69 plus TD, 0.5 in L, 0.5 in 0.69. This is S, and here's S. This is your controller. You got it, everybody? This is your controller. So implement this in your system, in your block diagram, or run it in Simulink. I said we have it in rare cases that we have such systems. Because when I said your num is that, means your y over x was this, guys, truly. S plus 1 to the power 1 cube. Means you have what? Means you have 3 repeated poles. P1 is equal to P2 is equal to P3 minus 1. We very rarely have such system. That's why Ziegler Nichols is good, but in some levels. Okay. Let me. Okay. Let me